Hello everyone, thanks for coming. I'm Mike Tonks, and as Jenny said, I work on the NTT team for Headforwards. Today I'm going to try and talk about WebAssembly. WebAssembly 1.0 shipped in March 2017, that's 2 years ago. Supported in all the major browser engines. So it's a prototype, working prototype release 1.0. We can use this now. So what is WebAssembly? Well, here's the official definition. This is possibly one of the worst product descriptions I've ever read. It's completely unintelligible. It's a binary instruction format for computer programs. It's designed to run in the browser. You can compile it from high-level languages like C, C++, and Rust. And what they're saying at the end here is it's not just for the web. This is not just necessarily targeting the browser. Some people think WebAssembly can be used for desktop server applications so that you don't have to worry about compiling for Windows, compiling for Mac, compiling for Linux. You just make one binary that runs everywhere. But for me, the interesting point is running in the browser. So I've made a simpler description. WebAssembly is a new browser technology that allows languages other than JavaScript to be used for making dynamic web pages. I was going to say for scripting web pages, but this is not a scripting language. This is a compiled binary format, so there's no script would be the wrong word here. So what does that look like? Well, web page with JavaScript. We've got our end user who sees a nice pretty web page. They don't care how it's built. Over here we've got a developer. He's writing HTML, CSS, JavaScript to drive that page. So what changes with WebAssembly? Well, we added a new option, WASM. HTML, CSS, JavaScript are unchanged. The experience to the end user is unchanged, but we've got this new option if we want to use it, WebAssembly. What that means for the developer is he can now build that WebAssembly using whatever tools he chooses to, or she chooses to use. We can use C++, C#, Rust, Golang, potentially any other language that comes along that can compile down to WebAssembly. Compiled languages offer a number of interesting options here. More choice for developers. This is great. If you're a Golang programmer and you don't like JavaScript, brilliant. We can write in Go instead. If you're a company that's got a huge set of assets already written in C, C++, well, you can compile it for WebAssembly and it will just run in the browser. Performance is supposed to be much better with WebAssembly. It's designed to be fast. It's designed to run in the browser. Better testing. Browser testing has always been a pain point. You've got to test it in Firefox, test it in Internet Explorer. Well, if you're compiling down to a binary, you can test this before you ship it. You should be able to write proper unit tests and CI without having to run Selenium. Make sure that your code's good to go. Strict data types. Well, most of these compiled languages have very strict types rather than using dynamic dictionaries. This means that we can enforce the structure of our data and catch a lot of common problems. And the same is true of the compiler. Because we need to compile that binary before deploying it to the web, the compiler will catch a lot of problems. And if you're running linters and code checkers, all of that should happen before you ship, which reduces the number of bugs in production. It's a binary format. Well, I'm quite in favor of open source, but there are definitely some advantages of not sharing your source code with your customers. I think this is going to be quite a game changer for a lot of companies. we'll look at the format in a minute, but effectively your users can't read your browser code, and that may be good in some cases. Reuse existing code. If we've got existing business logic and stuff in any of these languages, we can reuse that in the browser rather than having to also write a JavaScript version. So just a quick look. This is what WebAssembly really looks like. Don't worry if this is gibberish. On the left there we've got a short C++ function. Middle column is the binary, the hex codes that are actually shipped in that WASM file that's delivered to the browser. And in the right there we've got the assembly instruction. That's just an example what assembler looks like. This is not really a binary executable, but it's assembler, which is the next best thing. So what are people doing with WebAssembly? I've got a couple of examples for you. The first one is the Unreal game engine. This is probably one of the most famous 3D game engines, written in C++. Well, they compiled it for WebAssembly. This is just a demo. It's a little bit interactive. You can try this out online. When it gets to the bit with the fish, you can control. You can splash on the water. The fish follow the cursor. This is quite impressive, I would say. Another one is the Tonks demo. A really obvious use case of this technology is for games. And here we've got a little demo game. This one's written in Unity, so I think that's a C#. I think some of our people are playing with Unity already. Anything you write in Unity, you can build for WebAssembly. This is just a little Tonks game. It's a two-player game. Two people using the same keyboard. There we go. A third example, this is not really a demo, it's a bit of an advertising video. Qt, a big company, they make C+ libraries for making shiny widgets. I think they're quite excited about WebAssembly because now all of their customers, all of their tools which traditionally target desktop applications can now be compiled for the web. This is obviously just some of their demo widgets, but these things look pretty cool if we could have those in our web application. So what are people saying? Preparing for this talk, I did some research, looked at, there are loads of presentations, interesting stuff out there on the web. The first one is Thomas Nattestad from Google and LinkedIn, building the future of the web with WebAssembly. This is him. What has he got to say? Because WebAssembly was designed for speed, it offers better performance than JavaScript can. JavaScript is a dynamic language, which is great, making it easy to write. But it also means that the JavaScript engine has to optimize that code as it's being executed on the page. WebAssembly is optimized at compile time before it hits the browser, so it should be faster and more reliable. Since the web's conception, JavaScript has been the only fully supported option for developers who want to write logic for the web. But with WebAssembly, you now have more choice. Next guy is Dan Callahan. He's working for Mozilla on the WebAssembly team. The best part of this presentation, it's worth watching just for this, is this real-time video processing. This is an old project that's been done in JavaScript, but it stutters. Very impressive to do it, but a bit slow. They've redone the same thing in WebAssembly, and now it works seamlessly. I haven't got it hooked up so I can do it on myself through the camera, but It's worth watching his presentation just for that. So what's he got to say? He talks about the design goals for WebAssembly, why they made it in the first place. Bearing in mind there's a cross-company committee been set up. Microsoft are working with Google, working with Mozilla, are working with Apple to get this support into the browsers. So they've designed it with a purpose. Be as safe and universal as JavaScript. Run as quickly as native code. Provide consistent and predictable performance. So your code should run at the same speed no matter which browser it's on. Just because the Chrome JavaScript interpreter does a better job of optimizing your code, we don't want inconsistent performance between browsers. WebAssembly should be the same for all of them. And allow code reuse between the web and native. Full support for all major browsers was achieved in 1 year. This is actually quite incredible. New browser features take forever to get supported in all the browsers, but for the first time, working together, it took them a year to get the MVP into production. WebAssembly doesn't replace JavaScript, but does expand the web. Okay, Lynn Clark. Probably of all the things I've watched, Lynn Clark is the most inspiring. She does these great code cartoons and some really quite good explanations of complex points. The first slide is a quick history of JavaScript. This is the performance speed of JavaScript over time. It shows some significant points. Started around 1995 and it was slow. And remained slow. Some small improvements up until about 2008, where they introduced this just-in-time compiler optimizer in the browser. I think all the browser manufacturers did this around about the same time. Obviously, they need to remain competitive. This was because the use of JavaScript was really kicking off at this point when it needed to be faster. So that really improved things a lot. And there's a little peak there around the point roughly where Node.js came online. This JavaScript was now so fast you can actually do serious applications with it. And it's carried on improving as browsers have improved right up until the present day. What Lynn's predicting there is another upturn. With the introduction of WebAssembly, it's going to make things even faster. Another great slide. This shows what JavaScript does when it needs to execute your script, and ultimately why it's always going to be faster to use WebAssembly, because we've got to parse the code, we've got to compile and optimize the code, we've got to re-optimize it, which I think is this just-in-time thing where it tries even harder to execute, to optimize, and then only here does it start executing the code. So all of this bit, if you compile your code offline and upload the binary, we don't need to do this bit at all. That's become part of our build process. So moving on, WebAssembly 1.0 was an MVP. It works. We got this out into the browser. This is the minimum product we need to be viable for people to use. So what does it contain? It contains a compilation target for WASM, fast execution, small, compact file size, and linear memory. This means that tools like C that need memory management, tools like Rust and Go, they've got to be able to use that memory even though it's controlled by the browser. So there's some sort of memory stack there that these tools can use. This is the roadmap. So this shows moving on from the MVP. There's a lot more things in the pipeline. Some of these are already done. That's too small to read, so sorry about that, but you can look it up online. I'll run through it quickly. Over here we've got small modules interoperation. This means that you don't have to write your whole application in WebAssembly. You can write libraries in WebAssembly. This has the potential for things like React or Backbone or whatever JavaScript libraries you're using. If they need better performance, you can rewrite the library in WebAssembly but still use it from JavaScript code. You can also write WebAssembly applications that use those JavaScript libraries. So we've got interoperability. Over here we've got heavyweight applications. So this would be things like serious game development, or Office applications, the whole things that run in the browser. And down the bottom, I can't even read what it says. We've got compiled to JavaScript languages, and we've got JavaScript frameworks. So these are things that can benefit from WebAssembly to speed them up. So moving on, the next guy is Colin Eberhardt. He presented this at the JS Monthly in London and went on, I think, to present it at QCOM. WebAssembly and the death of JavaScript, one of my favourite presentations. There he is with his Superman t-shirt. So yeah, he asked, is this going to be the death of JavaScript? I think the answer is probably no. This is politically, this is a choice. But if you want to stop using JavaScript now and use other languages instead, you pretty much can. He also said, if you feel like throwing something at me, that's fine. Just wait till the end. Other technologies have come and gone over the last 20 years. Most of them have ended up failing. Maybe WebAssembly is just another one. We've had Java applets. People got excited about those. It turned out to be pretty rubbish. ActiveX, Flash. We're still using Flash, to be fair. Silverlight went nowhere. Dart, I've never even heard of. People are still writing games in Flash, but it's very likely that the next generation of those online games is going to be WebAssembly. Interesting. The way we're using JavaScript has changed a lot in the 20-odd years since it was invented. We're now writing a lot of JavaScript. Here's an example. npx create React app creates 79,000 lines of code. That's hello world. These days we're transpiling and minifying our JavaScript. We're processing it, we're building it. So the source code that we edit and the files we ship to the browser, they're not the same files any longer, apart from a few old school people like me. It's becoming the assembly language of the web. But JavaScript isn't a very good assembly language. Moving on, Johan Brandhurst, London Gophers, works at InfoSum. Get going with WebAssembly. This guy's a Go programmer. So with WebAssembly, we can write web apps without JavaScript. If you hate JavaScript, like you should, then maybe you can use WebAssembly instead. His quote. With Go 1.11, we can build WebAssembly in Go. So this was August last year they shipped. It's community contributed. It's not come from the core Go team. But I've been playing around with this and it's very nice. Golang WebAssembly files are currently really huge. And that's true. We found if you're writing a microservice in Go, it's brilliant. You get this really small binary relative to Python or whatever. We can ship these 10 meg, 20 meg files in our containers up to Docker or whatever. On a web server, this is nothing. But if you're sending that file to the browser, and we end up with similar 8, 10 meg files, it's too big. You can turn on gzipping, which might bring it down to 2 meg, which is much better. On a decent connection, that could be a 1 second load time, which is probably less than some of our JavaScript apps. But it's not great. This is the downside of WebAssembly and Go at the moment. Package level caching may save us in future, so splitting those files up, caching them, you only need to load the bits that have changed, maybe a solution. And he goes on, he does a nice introduction. If you want to watch this presentation, he talks through using Go in WebAssembly. The cool bit, he demonstrates gRPC web in the browser. So with that Go application, he's then talking to the server backend, not over Ajax, not over HTTP with JSON, but using gRPC, which is a binary format. So it's calling straight into functions on the backend. Yeah. This is potentially much faster and more secure. And I don't know if you can read that, but this is the request from his thing. So here we're sending octet stream. These are the function calls going back to the server. You can see it's not calling API users get, it's calling the get user method. Very interesting idea. So let's have a look at the code. Start off with, I built a WebAssembly widget. Video cannot be loaded. Perfect. It looks great. Well, I'm not going to switch to that. I took one of the Go examples. I didn't write it myself. There's some brilliant examples with thousands of points bouncing around. And it does that using SVG canvas. Built that, rendered it into a CMP widget, stuck it on the dashboard. Works really nicely. Added to that a couple of little buttons just to demonstrate the basic HTTP call. We need to be able to make those Ajax calls, talk to our backend. This all works fairly simply in a few lines of code. There is the code. It's on our Git server if anyone wants to have a look. And this is what it looks like. So I won't dwell too long on code, but you'll see this is what a GET request looks like. That's just making a HTTP call to an API. Bit of error handling. Check the response. And in this case, I'm just writing out, using the right method to put the name into the browser. The bit that actually interacts with the browser then, so we've got dom.getDocument, starting to look a bit like JavaScript. We've got doc.createElement div, setInner HTML, a getElement by ID for the target, and append child. So this starts to look like vanilla JavaScript. And there's a reason for that. It's because we're interacting with the same document object model. At the end of the day, those base APIs, instead of now being JavaScript functions, that you use the basic DOM as defined by the DOM spec. So we can do anything with that. Next step is to do a full page application. Video can't be loaded. It doesn't really matter. This is an operator page. So we needed an operator page for our next application. It's a very simple list view, pulling some logs back from the back end. No UI developers available, so we put together a prototype in WebAssembly. And it's very simple. Same sort of pattern. This is a full page application served up in from the object store. But when you want to get some system logs, you build a request using a request library and check the result. Here we've got a mouse event. So we're defining a on-click. When the button's clicked, then we go and do that request and call some DOM methods to write the data, build the display in the browser. I shared this with a friend of mine from one of the CMP teams, Charlton. And over the weekend, he rewrote it in Rust. The big win here is that Rust produces much smaller binaries. So where the Golang binary was 8 meg, the Rust binary was 350K. gzipped down, that's about 120k. And this is some example of the Rust code. It's a little bit more complex, but actually it reads pretty much the same. We're doing a request and writing the data back into the DOM. Here we go, there's a request, log request open, post, some API, set a header, another header, and do a callback when we get the response. As I said, this produces a much smaller binary at the end of the day. One of these is the WASM file. Can't see which one. Thank you, there it is. WASM loading in the browser. So, that's all very well. Why do we need WebAssembly? Well, it's faster, better, and comes with free beer. There are lots of reasons why you might want to use WebAssembly, but the one that appeals to me most is related to the Devops problem. Here we've been talking about this a lot over the last year or so, the wall of confusion between dev and ops, and breaking it down. Well, that's only part of the problem, because really we've got UI, backend, and ops, and we're constantly chucking things back and forth over these walls of confusion, and it takes forever to get anything done. Another way of looking at that problem, if you can see it, the contrast isn't great, is the Grand Canyon. There's an enormous chasm between these two camps. On one hand, we've got back-end developers writing Python, Golang, databases, Elasticsearch, whatever. On the other side, we've got the UI team doing HTML, CSS, JavaScript, UX. Great, but we're not brilliant at communicating. WebAssembly possibly bridges that gap. Just from playing around with those small examples, we've already got back-end programmers messing around, experimenting with the DOM, doing interesting new things. The other thing which is missing is joined up testing. We're terrible at testing our front and back end together, and it's always been a difficult problem. It's easy to write unit tests within one code base. It gets more complicated when you're trying to write integration tests even between back end projects that are slightly separated. Joining up testing with the front end is extremely difficult, and potentially having more of a shared code base across these things helps to solve that problem. And that's WebAssembly. Thank you very much.